Well, thank you. It's really a delight to be here. Joseph will appreciate this joke. He's an expert on sparse matrices too, so the sparse matrix, of course, is mostly nothing. So he and I are both we know mostly everything about mostly nothing. Right? This is a twist on. I normally do AX equals B all day. That's my professional career as I solve sparse linear systems using direct methods. This is different. And inside AX equals B, there's all kinds of interesting graph algorithms. But at the end of the day, I want to solve a system of equations. This is different. This is a project in which we're trying to use linear algebra over semirings to solve graph problems. So on the outside, the goal is to compute connected components and betweenness centrality and breadth first search and all these interesting graph problems based upon linear algebraic operations on the sparse adjacency matrices, matrix multiply and transpose and submatrices and such. That's the goal of this project. And it's kind of like, I like to think of it as a MATLAB for graphs. Very simple graph algorithms expressed in very powerful linear algebra. This is backed by a whole host of people. There's a steering committee for this API. There is an API committee. There's a group working on a project called LAGraph, which is akin to LAPACK, and it's a package of graph algorithms that's sitting on top of GraphBLAS, and because GraphBLAS itself doesn't even know how to do breadth first search. There's a working group for this. There's co-authors I have for this. There's also I'm collaborating in Julia. This GraphBLAS will shortly become the recommended way to do all sparse computations in Julia. Matrix multiply, transpose, submatrices, everything. And not just with the conventional linear algebra anymore. It's tropical, it's sparse integers, it's tropical algebra, it's max plus, min plus. And I'll explain what I mean by a summaring if you haven't heard that term before. We also have a Python interface. I'm working with Anaconda and NVIDIA on the Python interface as well. So there's a lot of people involved with this project, a lot of companies involved. NVIDIA, Intel, and Julia are all backing this. Redis as well. And then there's me right here. I'm just writing the code with a little bit of help. That's Reveille, that's our mascot. So the idea here is there's an observation that, for example, one level of a breadth first search is actually the same as a sparse matrix vector multiply. So let me show you how this works. This is the conventional classical breadth first search method. You walk through and you start by saying, okay, give me let's see, it's kind of hard to see my screen here. So the vector Q is a sparse vector that only contains one entry, just the source node. And then the parent is an empty vector, and then set the parent of the source to itself. So that's the root of the tree. That's initialization. And then in the traditional breadth first search, you basically go through this queue, grab a node, and say, who are your neighbors that haven't been seen before? So there's a flag there that says, there's an if test there that says, if you've not been seen, then do something. Add yourself to the next queue, and then set your parent to the one that discovered you, and then repeat. So this is the node edge centric way of writing a breadth first search. Very simple algorithm. And but the observation is that you can instead write this in about 3 lines of code using large scale bulk operations, which then give lots of benefits for parallelism. Here's the observation. You have the matrix here is the transpose of the adjacency matrix. So the 2 green columns are the outgoing edges of nodes 1 and 3 in the graph. So here we have a graph with, I'm doing a breadth first search starting at node 4, and I'm at level 2 at this point. Level 1 is the source node, level 2 is nodes 1 and 3. And so this represents, the dot is a 0, and just to make it easier to read. And the, let me move this pointer out of the way. There we go, that's better. The sparsity pattern here of this vector, whoops, I'm sorry. The sparsity pattern of this vector here represents the nodes 1 and 3 in the current queue. So now if we take the set union of the outgoing edges for nodes 1 and 3, we get what's in red. But that's exactly what a sparse matrix vector multiply would do in terms of the structure of the result. Now, numerically, I'm not getting the right numbers here. If you just do the conventional linear algebra, if you do that matrix multiply, you don't get the result with the values 1, 1, and 3 in there. So where are these integers coming from? This is really bizarre. I'll explain in a minute why I'm putting these numbers there. The idea, though, is that in the matrix vector multiply, you're just going to take these two entries in positions 1 and 3 here, and then do a operation where you're adding these two columns together, scaled by a multiplier, and then adding them to get here. So you see these entries in positions 2, 4, and 6 are the set union of these two columns. So that gives what's in red in the graph here, 2, 4, and 6. So that's the next level. Oh, but wait, I don't want to see node 4 again. So that has to be pulled out with an if test. But this is linear algebra. Where's the if test? This turns into a mask. And so this matrix vector multiply is what's computing the structure of 2, 4, and 6. And I'll get to the values in a minute. But then GraphBLAS has this notion of a mask. The idea of the mask is you have some matrix computation, and you want to assign it to the result, but there's a mask there. It says, no. It's size of the matrix. And you write an entry, and if it hits the mask says, no, you can't write there, or yes, you can write through the mask here. So the mask is a Boolean matrix of the same size as the output matrix that covers up parts that you don't want to write to. Here, the mask is complemented. It's a complemented mask. It's the parent vector, which says, if you have a parent, you don't get to write your result. In other words, if you've been seen already, you have a parent in the breadth-first search tree, so don't write that result. And so 4 would get kicked out. So the result of this through the mask would only be positions 2 and 6. So that describes the structure. So one matrix vector multiply gets to the next structure, the next level in the BFS. But now what are the values? Well, I also want to compute the parents of these nodes. The parent of node 2 is node 1. The parent of node 6 is node 3. So this gives us opportunity to use a summaring. And please, by the way, stop me in the middle if there's anything that's not clear. I'd love to take questions, because this is a real brain change and gear change in terms of looking at graph algorithms this way. It's powerful and expressive, but it's a completely different way of approaching graph algorithms. In a conventional matrix multiply, what do? Imagine you're doing it by dot products. Here I've not written as a collection of dot products, but imagine you're doing a matrix multiply written as a set of dot products. You take your finger down and you multiply pairs of numbers together, and then you sum up the answer to a single scalar. Well, what if instead of multiplying, you used a different operator? All it has to be is a binary operator. So that's the multiplicative operator of the summary. And then you get a bunch of numbers that you want to add together. Well, you could take the max, you could take the min, you could take any operator that's a commutative and associative operator with an identity element that can collapse this set of numbers into a single number. And that's what I want to see in the output. But here, this number's 113. I want to compute I don't want to multiply and add. I'd like to find the parent of the node. I'd like to find the node that discovered these positions 2 and 6. So this gives us a very strange summary. I call it the any second I summary. So the multiplicative operator is, that's the mask. So the mask level, I should say here, that if J is not seen translates into, if you don't have a parent, you can write to that position. So the any second I summary is a very strange summary. It's not a summary in a pure mathematical sense. There's mathematical definitions for a summary that this breaks. But we have an extended definition of a summary. The summary, the additive identity also has to be the multiplicative annihilator, the number 0 in particular for the conventional summary. Here, we don't have that in this particular summary. But here's the operator. The second I operator is an operator that does not depend on the values in the matrix, but its position. In other words, if I take AIK times, there's my multiplicative operator, times Q of K, I want to get the number K out of that. What? That's not the value. No, it isn't. It's the position of the entry in the matrix, and that's the result of the operator. Okay, so that's the multiplicative operator. And then what this does then, if you do this multiplication, this is position 1. If you multiply through here, say this second row times this vector, this value will multiply by 1 times 4. But the value is 1 because the K, the position, is position 1. The same thing will happen here. But here, the position is 3. So if you do the dot product and multiply these through, you find that position here in position 1. In position 3. So the answer is 3. What does that mean? And it's in row 6. That means that the parent of node 6 is 3. We discovered node 6 through node 3. So this gives me, this vector here gives me not only the structure tells me who's in the level 2, but the values tell me the parents of those nodes. So you get the tree, and then we just have to save the tree in Q. But, and I don't have this in this particular figure, what happens if 2 nodes, it's a set union, so 2 nodes could be both parents of a node. Well, it's a tree. I want to pick a parent. I don't want to have 2 parents. I want to add 2 parent IDs. That doesn't make any sense. If I have 2, suppose node 1 also had an edge, to node 6. Node 6 has to pick its parent, 1 or 3. I don't want to have 4 and add them. That's ridiculous. So I don't want to have an additive monoid that sums up the answer. That wouldn't make any sense. I need to pick one of them. Which would I pick? I could take the min, I could take the max, that would work. I could take 1 or 3, or I could just flip a coin. 3 it is, or flip a coin. I could pick arbitrarily. Why would I want to pick arbitrarily? I don't want to necessarily come up with a randomized algorithm for this, but I'd really like to do this in parallel. And if I'm computing this in parallel, I want maximal freedom to compute this result as quickly as possible. So pick the one that's fastest to compute, run it again, and it turns into a benign race condition. It's a non-deterministic operator, and I call it the any operator. Any of x and y is, so here's the result. Any of these two, any this of that, take your choice, and I get to pick. So if you call my function any of x, y, I'll pick x or I'll pick y, my choice. This operator is associative and commutative because you say pick any two. It's the same as telling me pick any two. It's also associative because if you tell me pick any two and then pick the third of the results, so you're using this as a reduction, it's also associative because in the matrix operation, I'm doing those operations for you. You're telling me reduce all these down to a single number. Basically, you're just telling, if the answer is, if I'm picking 5 numbers, oh, just pick any one, and there's your answer. So this is the any operator. It's also useful if you're doing the matrix multiply as a dot product. And then suppose that the operator was logical OR. That doesn't work here. But suppose you're using an OR reduction on a bunch of Boolean values. The moment you hit it true, you can stop. Well, with this operator, the any operator, it's only being applied to the set intersection in that dot product. If you have an entry that's present multiplied by an entry that's not present, nothing happens. The operator's not applied. So it's only applied to where the patterns match. And if you compute the matrix multiply as a collection of set of dot products, some operators can short circuit. They can stop the moment they find something interesting, like a true for logical OR. The any operator can stop at anything. So, oh, I found my parent. I don't need to go find the rest of possible parents. I can stop right now. So this gives this any operator a good chance for getting nice performance in a parallel algorithm. And on top of this, we have now a 3-line breadth first search that's also parallelizable because inside, you've given GraphBLAS the opportunity to do a lot of work here. I can take that chunk of work inside my library and do this in parallel. And now this is a parallel algorithm, whereas this is not. So this is an example. Now imagine what you can do in MATLAB with two matrices. You can add them, you can multiply them. You can do this in MATLAB. You can write a mask, and you can do a masked operation in MATLAB. That's supported. It's very slow for the sparse case. Element-wise multiply, this is like the Hadamard product or the dot star in MATLAB, but instead of dot star, it could be dot plus or dot max or dot min. In other words, the result is the set intersection of the sparsity patterns. And EYZ, it's the set union instead. And the operator used to combine could be any operator you like. So MATLAB's limited to dot star. Why not dot plus? I want the set intersection, but I want to add things that appear in the intersection. That would be like a dot plus if there was such a thing in MATLAB, but there is such a thing in GraphBLAS. And these are all very powerful tools for building up graph algorithms. All these other operations look like stuff you could see inside MATLAB. Extracting, get a submatrix, assigning where you have the indices on the left, apply a unity operator, select, it'd be like the MATLAB trill and true. You want to get a subset of the entries, give me all the positive edges, give me edges along the band, give me edges that suffice, that satisfy some property. One other thing about GraphBLAS is all of these matrices are stored in a sparse format, and I have to keep track of the sparsity pattern of these matrices, but all these matrices are opaque. The user can't see how I store them, so I get a lot of freedom to store them in any way I like. I just have to give the right answer. The other important thing about GraphBLAS is 0 is not special anymore. If you think about a graph problem, you may have an edge of 0 weight. That's very different than no edge at all. So if you're doing, say, some path distance problem, and you want to sum up path lengths, the edge that's not there is plus infinity. In other words, the additive identity value of the max operator is, or the min operator, I'm sorry, I get that backwards, is plus infinity. So the number not there is plus infinity, not 0. And these matrices, usually you think of a matrix, when you think about classical algebra with summer-rings, you think of a matrix with its entries living in a summer-ring, and you operate it within a summer-ring. Here with GraphBLAS, it's a little more free. You have a little more freedom in that the matrices migrate, if you will, from summer-ring to another summer-ring, depending on what you want to do at any given step in a graph algorithm. And so the entry that's not there, if you will, gets redefined depending on what summer-ring you're using. Yes. Oh, is there one in the chat? I didn't see it. Oh, I'm sorry. Yes, I will talk about GPUs. We're still working on it. Yes, we are working on actively collaborating on GPU kernels for doing all of this. And the upshot of it is that you will be able to write algorithms, whoops, like this, for example. This is in pseudo notation, pseudocode. This is all pseudocode, but you could write this algorithm, run it on the CPU. And oh, by the way, you have a GPU, and all you have to do is, when you initialize GraphBLAS, tell it, hey, use these memory allocators instead. And now you've got memory spaces that can migrate to the GPU. And then the rest of the algorithm is the same, and you don't know or care that you're using a GPU. It's just faster. It's that simple. You don't even have to say every operation, oh, by the way, use the GPU here. It's just all going to work. So we have these kernels working for matrix multiply, and we're trying to do a particular algorithm, triangle counting first. We've got a lot of kernels to write. And what we have to do to get the GPU working, and this would be good segue into this thing. I said that I could store these matrices in any format I like. Well, Joseph already described what I call the sparse format. It's compressed sparse row or compressed sparse column. An n by n matrix takes order n plus e memory, a dense vector of sparse vectors, basically. The matrix can be hypersparse. That extra size n vector can itself be sparse. So it becomes a sparse vector of sparse vectors. That is really powerful. So I collaborate with MIT, some guys at MIT Lincoln Lab that are using GraphBLAS to analyze internet traffic. And they just want to have a vast space of possible node IDs. And they want to build a matrix that's 2 to the 60 by 2 to the 60. It's really a big matrix. Now, but fill it with, say, 1 billion entries. So n is enormous. And you can't do this. And E is 1 billion, no problem. You can put this on an edge device. Literally, they have these matrices, 2 to the 60 by 2 to the 60 matrices on some edge device with a few million entries in it, and it works just fine. That's hypersparse, yes.
So what exactly does it mean by sparse vector or sparse vectors? Does it mean there's some columns or some rows that are entire?
Exactly. So what happens in a hypersparse matrix, you have a matrix where the most of the rows and columns are empty. And you wouldn't get this in a linear system because suddenly it's singular, right? But you get it in a graph. What if you want to have a graph of IP addresses? And the node ID is the IP address. You could map it down to a space of just the nodes, like 1 million by million if you have 1 million nodes present. But what if I want to let the node ID be the IP address? Exactly. Then you have a node with no neighbors. Exactly. It doesn't appear. Yeah, it's a singleton, but you don't need to store it. So, you know, in MATLAB, you can, for example, you can create a sparse vector that's a trillion by 1, a length 1. A sparse, that's very easy to do. Try transposing this, it'll fail abysmally. But with the hypersparse, it can do this without any problem. Because there's no order n time memory complexity in the data structure itself. It's just order E space, number of edges, and n can be larger than E. I also, and this is actually to answer your question about the dense case, and sometimes dense is better. I have another format called bitmap, or just 2 dense matrices. One dense matrix of the values, but I still have to record the presence of an edge or not. I can't cheat and put in an edge, yes. Right. No, yes, that's a good point. All the integer indices are 64-bit here. Yeah, I have to, because graphs are going to be big. They're not going to be limited by 2 to 2 billion nodes. That's too small. 2 billion by 2 billion is too small, which is crazy to say, isn't it? What? Yeah, yeah. Or 4 billion by 4 billion, it's too small. I am going to get back to the GPU question, okay? So I wanted to go through this slide and then I'll answer a little bit more about the GPU. So bitmap, it's just n squared, or m times n memory, with a dense Boolean matrix on top of it. Because I still have to give the right answer. I can't fake it and put an edge in and say, oh, well, the edge weight is equal to the additive identity of the monad, like put in a 0 and cheat. No. Because in a graph, a presence of an edge or not, whether it's weighted or not, is very different. I can't cheat like that. I have to preserve the structure of the problem as well as its values. And there's no special value that you ignore, like, well, let's ignore a 0. No, I can't do that. So there's the bitmap. And then full, if it's all present, I can throw away the integer space entirely. Each of these are stored either by row or by column. So that's already 8 formats. And each of them can be what I call iso-valued. Imagine spones of A in MATLAB. All the values are equal to 1. So in the MATLAB conventional data structure, what you would have is an array, integer array of the pattern, and then you have a double array, precision array of all the values. And what are they all filled with? 1, 1, 1, 1, 1. And it's boring, right? Why? Just have an array, it's 1 billion ones. Just cheat, have an array of size 1 and just say, if you want the value of the millionth entry, oh, it's 1. It becomes constant space in terms of the numerical values. That's called iso-value. And this kind of happens somewhat in linear systems. It happens a lot in graph algorithms, because how many times do you want to deal with an unweighted graph? A lot. What's an unweighted graph? All the entries are, well, ignore the entries, just look at the structure. Okay, put a 1 there, fine. But then they're all equal to 1. All the edge weights are, say, 1. So it's iso-valued. These matrices can be Boolean, any kind of signed, unsigned integer, float, double, complex. You can have user-defined types and operators, and then you can have thousands of semirings across all of this. Now, imagine pre-compiling a GPU kernel for each one of these cases. Literally, I think we've computed that we could probably compile more GPU kernels than there are atoms in the universe. So obviously, we're not going to compile them all. We have to compile them at runtime. So with NVIDIA, we're working on a JIT process. They have a JITify method in which we can construct a kernel based on the inputs to this function. We say, oh, you want to do that? Okay. I haven't done that before. Hang on, let me go compile the code. There it is. And then run it on the GPU, and then it's fast. Well, that took a long time. But next time, let me see, you want to do what? Oh, I've done this before. And you call it, and it's fast. So there's a lot of work to do for the GPU computing as a result. The other thing I have, so Joseph made a very good point about compressed sparse row and compressed sparse column being very slow to modify. You have to insert an entry in the middle of a sparse matrix stored in that format, you have to move all these numbers over to the side just to put one entry in. So if you ever try to do a loop in MATLAB where you just stick entries into a matrix one at a time, as to a sparse matrix, it's horribly slow. Because each time it's shifting the entire matrix over to fill in one entry. So I don't do that. It's all opaque. I can cheat. Nobody knows what my data structure is. So if you ask me, oh, Tim, set aij equal to 3. Oh, okay, thank you very much. I stick it in my pocket. I'll do it later because it's not there. I don't want to add it now because I have to. And you ask me again, oh, set A5, 3 to 42. Oh, fine, thank you very much. I'll stick it in my pocket and I'll do it later. So it's a lazy accumulation of these entries. So basically what I have then is a compressed sparse row format and the coordinate format, the triplet format of all these things, these edits that you've asked me to do. I'll just line them up, list them up in an arbitrary order. Well, they're not arbitrary, it's in order that they appeared. I'll just make them up, and I'll do them later when I have to. The same thing with deletions. I have a lazy deletion. Rather than deleting an entry and shifting everything in, I'll just tag it for deletion later. I call this a zombie. It's zombie in the sense that it's still among the land of the living, but it's dead. And well, the way I tag it, you can think of this as negating the index in the data structure. And so what happens is I can still do things like searching and binary search and such. And I have an entry in here. It's like a gravestone. It's got the name on it of what that entry was. So I preserve a nice ordered list of indices in a given row or column. And then I also have another lazy work in a compressed sparse row data structure. It's often the case, and Joseph showed this, that you would have, if you have a list of entries in a row, when you look at them, they're in sorted order of column index. And that's useful. If you want to find a specific one, you can use binary search. If you want to add two vectors, you can do a merge, like an merge sort. It's handy in some graph algorithms to have your matrices sorted. So I keep them that way until I don't, and I cheat, because maybe the next operator doesn't care. And so I have a flag that says, hey, this matrix is jumbled. Are you good? Yeah, I'm good. I don't care, and I'll use it anyway. And you can then sort later when you have to, if you ever have to. So this gets complicated. This package is about 100,000 lines of code just to do these things. And the GPU kernels have to be computed on the fly because there just would be too many of them. So here are a few more algorithms using interesting semirings. PageRank, for example, is the conventional semiring, except the multiplicative operator is not plus times. It's plus second, where second is not the positional operator. The second operator is f of xy is y. It's like, why would you want such a silly multiplier as, I mean, f of xy is x times y. That's the conventional linear algebra. Here, f of xy is just y. And you might ask, why? Well, it's sort of like saying, yeah, I don't care when you're doing PageRank, you don't care about the edge weights. if it's got an edge, you want to treat it as if it's a 1. So you might, in MATLAB, write, oh, I want to work with A equals spones of A, and just replace all the entries with 1. But then think about what the multiplicative operator is going to do. Multiply is going to take x times y to get a product. The x's will always be 1. So just stick in y. And that's the second operator instead. So it can basically see a weighted graph and say, yeah, just ignore the edge weights. Treat them as if they're equal to 1. And that's faster because I don't have to load the edge weights either. So you save a lot of memory traffic. Triangle counting is a 3-line or 4-line. You take a lower and upper triangular matrix, and then you use a +1 semmering, because you're counting intersections when you're doing triangle counting. A triangle is a clique of size 3 in a graph. And in triangle counting, what you want to basically do is you're looking for 2 nodes. Do they share a neighbor? If there's an edge there, do they share a neighbor? If there's an edge there is where I want to compute the answer. So it's a mask, which is the matrix itself, L. L is the mask here. And then the triangle count comes along and says, let me find the size of the intersection. They have an edge here. How many of these 2 nodes, how many neighbors do they share in common? That's the count of the triangles. Well, I'm only doing is counting. I don't want to actually look at the edge weights. I just want to see what edges are there. So this is an operator, f of xy equals, the multiplicative operator of this semmering is f of xy equals 1. Just 1. And then the monoid is also just plus because I want to sum them up. So once you see this semmering, it's like, wow, that just blows your mind. That's so beautiful. A +1 semmering. All right. K-truss is very similar. Sparse deep neural network. This was fun. This is the ++ semmering, because you want to do this matrix multiply with the conventional plus times algebra here, written in pseudocode, followed by a bias. And basically what you want to do is you want to take any entry that's present in this sparse structure and say add some scalar to it for this whole column. Add, not multiply. Now, if it was multiply, you could think of this like A times D, where D is a diagonal matrix, and that scales the columns. I want to scale the columns, but not with a multiply operator. I want to scale the columns with a plus operator. So it's the multiplicative operator is plus. So it's the ++ semmering to do that. This code, this is a terse version of the code. It took me 20 minutes to write in the C API, and it was 100 times faster than for the specification of the problem. And it's parallel. This is a little more complicated problem called single source shortest path with delta stepping. And I don't have time to go into the details of this algorithm. But what I've highlighted in green here is really powerful. Basically, what delta stepping is doing, it's taking the graph and splitting it into 2 parts, edges that are short, edges that are long, below delta and above delta, for some input parameter delta. So the graph is split into 2 parts. Now the matrix is the sum of these 2 parts, and there's no overlap. Then what delta stepping does, it has an interface where you're only looking for paths that change by that step size times delta, or in that length. And the outer loop is going to the next bucket of path lengths. So it's walking through the graph by path lengths. This algorithm for both of these multiply operations here uses a min plus semmering, because what you have there in the vector, which is the vector t masked here, it's the best known path so far, the length of the best known path so far. And in an edge relaxation step of a single source sort of path algorithm, you take that path you have so far and you look at an edge and you say, well, if I have a path to here and an edge from I to j, can I make the path to j shorter using that route? So you have then 2 paths you're considering and an edge to get to the target node. So you want to ask, well, who's better? the original edge that I had before, or the other path, I'm sorry, the first path I had already, or the other path plus one edge. Plus one edge is the plus of the semiring. So it's the min plus semiring. So you have the vector containing the path length, add an edge, and then you want to find the best one. What's the best one? The min. If I have a lot of possible options, I want to take the min. And so the monoid is min plus. It's a tropical algebra. So in one step, in one matrix multiply, matrix times vector, you can work across a swath of the entire graph. And you're calling GraphBLAS, and I've got thousands of lines of code to do all this in parallel inside, where it's all the complexity is inside. And the algorithm, this is almost as detailed. In fact, what I did to do this, to put this slide together, I took my algorithm for single source shortest path in LA graph that used GraphBLAS, and I just left the comments. These are the comments. The lines below it are the one line, each is one line call to GraphBLAS. So if I wrote the GraphBLAS for this, it'd be just as long as this. It'd just be a little bit harder to read because you're calling C functions to do every step instead of what you see up here in this notation. But it'd be just this, about this long in terms of piece of C code. It's about a couple pages long with comments and extra stuff at the header and error checking and things like that. No, it's not Floyd-Warshall. It's a thing called delta stepping that allows you to, let's see, Floyd-Warshall, wait, isn't that hold on, isn't Floyd-Warshall all pairs shortest path? No, it's single source. I always get it mixed up. It's single. What's that? It's all, isn't Floyd-Warshall all pairs? Yeah, Floyd-Warshall is all pairs. Yeah, all pairs would give you a dense matrix. And that's gonna be costly. I do have a Floyd-Warshall algorithm, actually, that a student wrote. This is single source shortest path. So it's Dijkstra's or say, this is like a Dijkstra's algorithm where you have a heap of nodes and you pick. But see, Dijkstra's is sequential. You have the tree so far, the paths you have so far, and then you have a frontier of nodes you haven't seen, and you pick the node of the best frontier, and that's the next added term to your shortest path tree. And then you repeat, you do the relaxation, you repeat. Each relaxation, that will be one edge at a time. So it's very sequential. This is parallel. Delta stepping is parallel because it's processing the entire graph in a bulk. And so delta stepping is very amenable to GraphBLAS. The thing about GraphBLAS is if you have an algorithm, a graph algorithm that's expressible in terms of in parallel, then it'll often be easy to translate to GraphBLAS. The breadth first search, for example. If instead you have an algorithm that's hard to do in parallel, it's probably also hard to do in GraphBLAS. Like depth first search. I was like, oh, I really love to have a GraphBLAS depth first search because it's so fundamental. I don't, because it's one edge and then you come back and do another edge and come back, and it's one at a time. You can't really do it as a big, large, bulky thing. But this algorithm for single source shortest path, you can, but Dijkstra's you can't. So it's a parallel kind of variant of single source shortest path. So we have this wrapped in, there's a C API. We have this wrapped in Python, Julia, MATLAB. In fact, it's already built into MATLAB, but just for one operation, A times B. So Jim was asking about multiplying two sparse matrices together. MathWorks has used my code for that for about 15 years. It was single threaded. Last year they announced, oh, it's faster now. That's because it's now using GraphBLAS inside. So GraphBLAS now is in your laptop if you have the latest MATLAB, but only unfortunately for A times B. They need to do it for more, but it's not there yet. But for Julia, I'll show you, it's really going to be blazingly fast with this. Here's the different kind of syntax, what it looks like. Suppose you want to do C with a mask. There's the output. We also allow for accumulator operator. This is like the plus equals of C. So this is like C equals C plus. And then here's A times B with the min plus semiring, let's suppose. The C function for this, you just have to specify all these parameters. There's the C matrix, the M, there's the additive, I'm sorry, the accumulator, there's the semiring, and there's the two input matrices. Python, you can do with all of its glory, you can do this. Julia has, Python also has a very simpler way if you don't need all these extra parameters. Here's two ways of doing it in Julia. There's do a multiply of these two matrices using the min plus semmering, please. And that's it. Isn't that beautiful? That's like, wow, I love that. Oh, you can write it as the functional form as well. And in MATLAB, this is my MATLAB interface. This is an object. I have an object-oriented interface to this. You can write this, or you can literally write A times B, but I assume the conventional summering in that sense. So this might be too small. Here's some more examples of different syntaxes. Maybe I'll jump through quickly this. But here's some of the algorithms we can write. This is PageRank in both Julia and Python using GraphBLAS. And I don't want to go into all the details of what's happening here, but this is the entire algorithm. This is nothing left out. This is PageRank. Julia, it's here, the plus second semmering I talked about. In Python, there's that plus second again. Joseph mentioned betweenness centrality. This is a two-page code for betweenness centrality. Betweenness centrality is a bulk breadth first search, basically. Betweenness centrality asks the question, there's a node there. Is it important? Well, if the shortest path from this node to that node steps on this node, then that node I stepped on gets bumped up in importance. It's a metric on how many shortest paths go through any given node for all pairs of other nodes. Now that's expensive to do it for all pairs. So what we do instead is approximate it. You pick some random set of source nodes at random. Here's one, here's another one. And then you do a bulk breadth first search through the whole graph and you count, oh, I see you. You count, and then you walk back and sum up the results. So it's a breadth first search followed by a post-processing step. And this is the algorithm in Python and in MATLAB. First stage and second stage. And the comments here are describing what it's doing. We're walking backwards, looking at the kth frontier, and taking that betweenness centrality metric and / dividing it element-wise by the path, and so on. And there's another matrix multiply, and so forth. And there's the details at the end, summing up the centrality at the end. Now, I don't want to go into all the details of the algorithm, but what you can see here is it just looks like just flat out linear algebra. It's simple to think of, it's simple to reason about. For some summer rings, A times B equals B transpose times A transpose, quantity transpose. In fact, that's always the case. Matrix multiply doesn't always distribute depending on the summer ring. So you have to be careful with that. Across, say, A times the quantity B plus C is not always A times B plus A times C. If you don't have a multiplicative, if you don't have all the full properties of a formal summer ring, like that weird one, any second I, that's not going to be distributive. But this is very elegant. There's no parallelism here. This is blazing fast. In fact, this is so fast, it beats this code. This is from the GAP benchmark. This is a code that's written special purpose C++ just to solve betweenness centrality. And it's write once code. I mean, only the expert would understand this code. This is not code that you can explain to somebody. I mean, it's fast code, but it's impossible for an average data scientist to write. But guess what? This code for a large graph problem versus even in Python, here's the performance. This is GraphBLAS using that elegant code I showed you. Is 31 seconds or 23 seconds in green here, these numbers. This Kronecker matrix, it's 30 seconds with the code that's hard to read. So the code that's hard to read is actually slower in pure C++. It's actually slower than this elegant thing in Python. Now, I don't always win like this. This is of these results, so they only have these 3 cases where it's actually faster, but I don't always need to be faster. I like to think of this as I'm building graph algorithms with Legos. I built a race car with Legos, and I beat a real race car here for those 3 cases. If I am just twice as slow as the race car, but I built the thing with Legos, and I could write it in a day, then I'm happy. So breadth first search, sure, I'm a factor of 2. The algorithm I showed you with breadth first search, I'm maybe twice as slow as an incredibly well optimized BFS. This is not a slow parallel. This is a very fast parallel BFS. And I'm only a factor of 2 slower than a special purpose drag strip racer. But GraphBLAS, it's like a Porsche Cayenne or something like that. You can take your kids to soccer. You can take it on the track, but you can also take your kids to soccer with it and put groceries in it. It's street legal. But the gap benchmark's not street legal. You wouldn't use it in production. It can be slow. There's a reason for this. It's because there's some overheads. It's a graph with very, very high diameter. So I don't win all the time. Page rank, triangle counting in red where I'm significantly slower. So it's about a factor of 3 here. And there's a reason for that I could make do better. And that is in the next slide. No, next couple slides I'll explain. Here, single source shortest path that I showed you a little bit longer. It's maybe 4 times slower than a special built method that doesn't use GraphBLAS. So we've got work to do to build up the performance, but I'm only a factor of 4 away from an extremely well-designed parallel single source shortest path delta stepping algorithm. And I've got 13 minutes left. Jim asked the question, how do you do matrix-matrix multiply? Well, this gets complicated. It's about 10,000 lines of code, not including 300,000 lines of code that I generate for 1,500 summer rings. When you're multiplying 2 matrices together, 2 sparse matrices together, you saw from the BFS what you want to do. One way of doing it is what's called a sparse Saxby operation. You have this sparse vector, and suppose there's just 2 entries in that sparse vector, and you have a sparse matrix stored by column. What you can do is take those 2 scalars and grab those 2 columns, scale those 2 columns by the multiplicative operator, which could be times if you like, conventionally, and then add them together. So it's a set union. The sparsity pattern becomes a set union of those 2 or more. If you have 3, it'd be the union of the 3. So that's the method to do that is called Gustafson or hash method. It's a Saxby style method, but how do you do the set union? One way to do it is have a vector of size n, it's workspace, where you can stick stuff in and then compute the set union that way. And that's Gustafson's method. But doing this in parallel is costly because every thread would need its own workspace unless they cooperate. And that's what I call the fine Gustafson method, where all the threads use a single workspace, but now we need atomic operations to grab this because we could have multiple threads grabbing the same thing. So I have a suite of different methods to do this. And one of the ways I use this is every little entry in the matrix in this workspace has a tiny little finite state machine behind it, because I also want to exploit the mask. So that mask is powerful. It's powerful. It's expressive. Like if you don't have a parent, don't write there. But what happens if you're doing a matrix operation and you want to pipe it through the mask? You can look at the mask and say, well, wait, you don't want me to, you're not going to use this number? Well, I'm not going to compute it. So you can prune the work out of that matrix operation, only to compute the numbers you need that will fit through the mask. So we'd like to exploit the mask during the factorization. So if the mask is present, then just ignore it. The state doesn't, this entry, we try to write it, oh no, don't put it there. Otherwise, the finite state machine handles the atomic operations for modifying this operator. And I'm running on time, so I'll skip through this. Parallel assignment, let me jump through this because I want to show you some other things. This gets really complicated. To assign, this is just like Cij equals A in MATLAB, where these are index vectors. So you're taking a submatrix and putting it into another submatrix. Let me just jump through to the punchline. And here's the punchline. A times B, sparse times sparse. So how well, okay, Can we do graph algorithms? Yes, sometimes I'm slower, sometimes I'm faster for graph algorithms. But what about the core matrix operations themselves? Let's compare with MATLAB. A times B, sparse times sparse. I'm actually beating myself because I wrote the code in MATLAB 15 years ago, single-threaded, but now it's 30 times faster. And even in the current version of MATLAB, they're only using GraphBLAS version 3. I'm up to GraphBLAS version 7. I'm beating myself by the factor of 2. Okay, Cij equals A. And literally, you can write that same syntax. I have operator overloading. If this is a GraphBLAS matrix, then it's the same syntax, just using GraphBLAS matrices, not MATLAB sparse matrices. And it's 1,000 times faster, up to. You can compute these. You can't do this in MATLAB. You can't compute, I'm not pointing with my pointer, but the Zoom people can't see this. You can't do this in MATLAB. But you can do this, no problem. It's hypersparse. This is absurd. Those what? 1, 2, 3, 4, 5, 6 character syntax. C of M equals A. All this does is if Mij is true, assign Aij into Cij. That's all it does. This is a built-in operation in MATLAB. It's the mask in GraphBLAS. It's the same thing. Oh, cool. MATLAB has a mask. Let's use it. And then I wrote this MATLAB interface and tried out my mask. Oh, it's working great. Now let's compare against MATLAB. And it took me a second to compute this expression in GraphBLAS with GraphBLAS matrices, 5 days in MATLAB. Literally, I let my laptop run. It actually did finally finish the answer. It's the difference between an order n squared algorithm and n log n, where n is the number of entries in the matrix. It's e squared versus e log e, basically. I'm doing e log e in less than a second, where e is a billion. And they're doing a billion squared. That's a big difference. That's a factor of 500,000 speed up. So it works in MATLAB, it's just there's a performance bug. Other things like sparse times full. Now, I do direct methods, right? Guess what, Joseph? I'm going to speed up these iterative solvers now. In fact, because sparse times full is so important in iterative solvers, and I'm 10 times faster now than MATLAB. So now and in fact, because of my operator overloading with my MATLAB interface, you can just pass to the built-in MATLAB GMRes, pass it a GraphBLAS matrix instead as an object, and it all works. And my matrices can be, say, single precision. So now you've got GMRes and single precision, just like that. And it's faster, not just because it's single, because it's also parallel, whereas MATLAB is not. So it's very exciting. You can just drop it in and boom, it just goes. Full-time sparse, transpose 10 times. Even adding, Joseph mentioned adding 2 matrices. It's a simple thing, right? Well, now do it in parallel. It's a little harder. And MATLAB does not have a parallel add. So I'm 10 times faster there. What about maybe a better matrix library? What about the Intel supporting this work as well? So they're very excited because I'm beating the MKL sparse package for them using GraphBLAS. They're supporting it. And these are MKL conventional linear algebra now methods like sparse times vector, sparse times matrix, add 2 sparse matrices, add the transpose and just transpose. These are the MATLAB when you say do say A transpose times B, they'll look at this and say, oh, I need to transpose you. They'll transpose it and keep a copy inside the A data structure for the A matrix. So it's there the next time they want to use it. So the second operation can be faster. And they also do some pre-analysis and they cache it inside the matrix. I don't have such a warm-up time. I just go straight, solve the problem, and then forget what I just did. So here's my run times for this matrix. This is a large, this is all of Twitter is the graph. It's a big graph. Who follows who in Twitter. And you can see the MKL runtimes in the speedups. It's 2 to 8 to 21. And I didn't show you the place where I am 70,000 times faster than MKL. But that's a special case, so I didn't bring it up. On top of GraphBLAS, so I basically have a very high performance sparse anything package with any kind of operator you want, any kind of data type you want. In fact, even user defined types. I've got an example at runtime. You can tell GraphBLAS to create a user-defined type. For example, I've got a case where just for fun, I said, well, this edge weight is going to be a 4x4 matrix and a 64-character long string, because why not? And then define operators based on that, whatever operator you want. It's just a C function that's going to take two values and do something to them and produce a result. And then you can wrap that in a subring, and I'll say, sure, you want that subring? That's weird, but I'll do it. And I do it without having to even recompile GraphBLAS. GraphBLAS itself is a tool for writing graph algorithms. It's also a good tool for doing sparse scientific computing as well. But it doesn't have any graph algorithms in it. That's the goal of LAGraph. LAGraph is a package we're running on top of GraphBLAS to solve interesting graph problems. So we have these algorithms. This is the gap benchmarks. We have lots of these methods they've written that are not quite polished enough to say that they're ready for production use, but they're working. They're fairly decent performance, many of them. Like counting all size 4 graphlets. Go through the graph, and anytime you see a clique of size 4, go to those 4 nodes and say plus tick, 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 increment, because those 4 nodes are participants in a clique of size 4. And then there's like 16 different kinds of these little 4-node graphlets. And sum up, okay, node, how many graphlets are you in that consist of a triangle, a clique of size 3, plus an edge going out like that? How many, node? Node, how many about you? What about you? So every node gets 16 numbers. It's a very useful way of analyzing a graph for these little tiny structures to ask interesting questions about the graph structure. That can be very easily done in GraphBLAS. K-truss, Bellman-Ford I mentioned, finding an independent set, lots of really cool algorithms we can write, and we're just writing more as we go along. Lots of connections with lots of ways that GraphBLAS is being used, and I've got 3 minutes left. Let's see. It's in a package called RedisGraph, a database. It's in Anaconda. They're supporting the work. They're working with me. It's in every Linux distro. It's built in. It's part of my SuiteSparse library, which gets plunked into every Linux distro. It is in MATLAB, but just A times B only. It's in Julia now, and it's going to be the recommended way to do sparse matrices in Julia, all of them. So, which is really cool, because now suddenly Julia has access to all these submarings, but it's also really fast and parallel for, I've got some performance metrics I thought for Julia. I guess I didn't. Now, the same level of speed up we're seeing in MATLAB, we're seeing in Julia as well. So now Julia is 2, 5, 10 times faster, or 1,000 times faster for some cases than the previous sparse computations. RedisGraph is a graph database built on top of GraphBLAS. And here's an example of a guy giving a talk from a company called MD Metrics. This little plot here, they do hospital analysis, data analysis, and they want to reduce opioid usage. So they use RedisGraph, which underneath the hood is all this GraphBLAS stuff, and they're getting all this cool data analysis done to cut down opioid use. And that plot just says it's almost going to 0. So I'm solving the opioid crisis just like that by doing linear algebra. I have no idea how I'm doing that. Don't ask me. Lots of things in progress. LAGraph is coming along. GPU acceleration, I already answered that question. Julia integration is almost is ready for production use. It'll be announced on the Julia computing blog within a week or 2. We've got the Python interface, RedisGraph. I want to put in a JIT on the CPU side. I want to also use aggressive non-blocking. There's a thing called non-blocking mode in GraphBLAS. Let me jump ahead to that. And I'm out of time. It's 10:30 on time. Let me wrap it up. With non-blocking mode, remember GraphBLAS has this lazy evaluation stuff. I can say, I'll do that later. Thank you very much. I can do that across calls to GraphBLAS. So you could call GraphBLAS multiple times, and I could just be writing a note. Do you want to do that, and then that, and then that, and that? Okay. And then later, when you want the answer, oh, hang on, I haven't actually computed anything. And then we look at these operations. I haven't done this yet, but you can fuse these operations together and say, well, oh, I recognize that. I have a special way of doing these two operations fused together, and then you get a faster algorithm asymptotically. So that's what this is looking at. So in summary, last slide, GraphBLAS, strengths and limitations. You don't write matrix multiply with a triply nested loop, right? But think about the way you think about it, look at a typical graph algorithm. It's got these little bitty nested loops, right? Don't have to do it that way. You can hoist it up to the level of linear algebra. Simple high-level API with bulk operations, with good scope for parallelism, very simple algorithms, possible fusions. It has some asynchronous features which are interesting. No loss of performance in Python and C because it's very bulky operations, and the overhead of calling through Python is very lightweight. And it's beating SuiteSparse, it's beating MATLAB in a vast way. The performance can rival, maybe with a factor 2 or 4 away from a highly tuned, but sometimes it can actually be faster. And I could explain why that case is faster. Limitations, there are no triply nested loops. That can be a limitation because the depth first search, for example, you'd write it as a bunch of nested loops, and it's not hoistable up to this level. And that's hard to do in GraphBLAS. Some algorithms are hard to express, depth first search. And then I haven't done like fully asynchronous methods. There's a way of writing PageRank with Gauss-side L, for example, if you know what that is. I can't quite do that in GraphBLAS yet. So there's some asynchronous behaviors I can't exploit, and some I can. So that's GraphBLAS, graph algorithms in the language of linear algebra. And so this is a linear algebra conference. I'm speaking your language. Thank you. Do you have any further questions? There was a GPU question, and then, oh, a Julia question. The answer is yes. If I say C equals S times F and Julia does it automatically, I love that. Run your code. All you need to do, I'm not a Julia worker yet, but I will be. Do I need to call a special GraphBLAS function? No, all you need to do is like using, what is it? Is it import or using? I forget. Instead of using sparse arrays CSC, it's using SuiteSparse GraphBLAS, and you're done. So suddenly these objects, this matrix A or S or F or whatever, they suddenly change from being Julia sparse arrays CSC is the data type. They're now a GB matrix. And then you can do times and plus and transpose, and everything works. All your codes just work. But then you can do cool stuff like, oh, I'd like a different sum array, please, which you can't do in Julia right now. And now you can. So it's a very trivial change to a Julia code. Yes, Joseph. Is MATLAB going away? I think we should move to Julia rather than Python myself. It's faster. Python is powerful, but it also struggles with very fine-grained computation. Julia doesn't. Otherwise, at the high level, Julia and Python have equally expressive and beautiful ways of calling GraphBLAS. MATLAB, I mean, if I were to be able to dig into the guts of MATLAB and pull stuff out and put stuff in, then it could just be just the same. For example, in MATLAB, you could write this loop for say k equals 1 to 1,000,000, generate a random integers, do aij equals x, and just stick an entry in one at a time. That's incredibly slow in MATLAB right now. If that matrix was a GraphBLAS matrix, it'd be blazing fast. Because all I'd be doing is making a coordinate list internally. And then now I want to work on the matrix. Oh, it's this triplet. It's all these pending updates. Hold on, let me build the result and go. And that's the way you're supposed to build a matrix in MATLAB. But I would just be doing it under the hood. All this performance gain that you see here, there's no reason, you see, this should be 1x, 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 1x. It can be easily all of that. There's no reason it can't be. I just don't write MATLAB. I mean, I don't have the gut internal, I'm not the person who goes inside MATLAB and pulls out a sequential code like, what's this matrix multiplies? Who wrote this? It's single threaded. It's awfully so. Oh, Tim Davis wrote that. Let's throw that away and put in GraphBLAS instead. That's code I wrote 15 years ago. They've already thrown that away. They have GraphBLAS in there, but now they're on GraphBLAS 3. They're not on GraphBLAS 7. So I don't think MATLAB is going to go away. Do they want this level of performance? It's there if they do.